Hello, and welcome to this presentation, Getting Started with the RTB2000 Function Generator. In this presentation, we'll walk you through how to use the function and pattern generators on Rohde and Schwarz RTB2000 series oscilloscopes. Option RTB-B6 enables the creation of both predefined and arbitrary signals. These can be used for a wide range of applications, such as during design, testing, and debug. It's also very helpful for training or educational purposes. There are actually two different types of generators enabled by this option: a single-channel function generator, as well as a multi-channel pattern generator. In the remainder of this presentation, we'll show you how to configure and use both of these different generator types. Both generator types are selected using the RTB menu. The generator signal is output using the aux-out connector on the front of the RTB, and the pattern generator uses connectors P0 through P3. Note that if you're connecting the aux-out directly to an RTB channel via coaxial cable, you should change the load parameter from the default 50 ohm to high Z or high impedance. Let's start by looking at the function generator. The RTB function generator can create a wide variety of signals, such as sine, triangle, ramp, etc. If you're unsure of what each type is, note that a small graphical representation of the selected function is displayed at the top of the menu. After choosing the function you want to generate, here we're using sine as an example, there are other parameters that need to be configured depending on the function type. The most fundamental parameters are frequency and amplitude. Activate is then used to output the waveform. Let's start with four of the most basic functions. DC simply outputs a constant voltage at the defined offset. Sine generates a sine wave with a given frequency and amplitude. SinC is a classic sin x over x function, and rectangle produces a rectangular or square wave. Offset and noise can be added to most waveforms. For example, we could add a voltage offset to our sine wave to shift the waveform upwards or downwards. And we can also add a user-defined amount of noise to the output waveform. For triangular waveforms, the symmetry must also be configured. A triangular wave with the default 50% symmetry has rise and fall times with equal slopes. In a triangle with 10% symmetry, the signal is rising during the first 10% of the period and falling for the remaining 90% of the period. The opposite is true for a triangle wave with 90% symmetry. It rises for the first 90% of the period and falls during the remaining 10%. There are two special parameters when it comes to configuring pulsed signals, the first of which is duty cycle. A 20% duty cycle, as shown here, means that the pulse is on for 20% of the time and off for 80% of the time. Since our frequency is 1 kHz, this means our total period of 1 millisecond contains 200 microseconds of on time and 800 microseconds of off time. The second important pulse signal parameter is edge time or rise time. This is just the amount of time it takes for the signal to transition from the high or on state to the low or off state, or vice versa. In the first example, the edge time is 50 microseconds. Decreasing edge time creates more rapid transitions, that is, more vertical pulse edges. For both ramp and exponential waveforms, there's an additional polarity indicator that determines whether the waveform starts low and goes high, as shown in these screenshots, or whether the waveform starts high and then goes low, as shown in the screenshots at the bottom. A final basic parameter is invert, which simply swaps or inverts the high and low states of the configured waveform. Sweep can be used to dynamically vary the frequency of a generated waveform. The start and stop frequencies and the sweep time are specified, and this causes the frequency of the waveform to be swept across this range of frequencies. The sweeping can be done in several ways, such as a linear sweep that goes from low to high and then jumps back to low, or a triangle sweep that ramps the frequency from low to high and then ramps back down from high to low again. Burst mode is used to output a waveform a certain number of times, either once or continuously, with pauses between each burst. For example, using a sine wave as our function type, we enable burst and set the number of cycles to 5. The RTB generator outputs a burst of 5 periods of the sine wave signal. Because the trigger is set to manual, only a single burst will be sent each time the manual button is pressed. If we change the trigger type to continuous, the burst will be sent continuously, separated by the specified idle time, here 5 milliseconds. In addition to the basic waveforms we've already discussed, the RTB function generator can also add 4 different types of modulation to the generated waveform, namely amplitude modulation, frequency modulation, amplitude shift keying, and frequency shift keying. We'll show how to configure these on the RTB, but separate presentations are also available if you'd like a more technical introduction to each of these modulation types. Using a 1 kHz sine wave as our unmodulated signal, we can see the effect of adding amplitude modulation. Here, the signal amplitude rises and falls at a rate of 1 Hz. As before, triangle means the amplitude rises steadily and then falls steadily, and the modulation depth can also be specified. In the case of frequency modulation, the frequency of our sine wave is being changed using the user-supplied values of frequency and deviation. In amplitude shift keying, both the frequency and the ASK depth need to be configured. Frequency controls how far apart the high and low states are, and depth controls the difference in amplitude between the high and low states. In frequency shift keying, the hop frequency is the amount of frequency shift between the two frequencies, and FSK rate is how often the shift occurs. Again, please see the separate technical introductions on ASK and FSK if you'd like to learn more about these modulation types and their modulation parameters. Next, let's talk about arbitrary waveforms. An arbitrary waveform consists of a series of user-defined points, and, as the name implies, these points can be used to create any arbitrary shape. On the RTB, these points can either be loaded from a file, or can be created by copying all or part of an acquired waveform. Let's start by looking at this second case. The arbitrary setup menu is used to create an arbitrary waveform from an acquired waveform. Source is used to select the channel from which to copy the acquired waveform. Cut waveform is used if we want to select only part of the acquired waveform, and copy is used to load the full or cropped waveform into the generator. Let's go through this process step by step. We'll start by acquiring or capturing a waveform. This is usually done using a single triggered acquisition. If we only want the rectangular signal or pulse, we would choose Cut Waveform. The part of the waveform that will be cut is shaded in purple. We can select this area in a number of ways. For example, we could use the touchscreen to slide the cut markers manually. We could specify start and stop times. Or we could let the RTB set these limits based on the automatically determined period of the signal. Once we've copied our waveform, we can use the Visible switch to display the arbitrary waveform on the screen in the form of a purple trace. Note that the waveform will be stretched horizontally across the entire screen for ease of inspection. Once the arbitrary waveform has been loaded, we simply enable output to start generating the arbitrary waveform. As with the other waveform types, we can specify frequency, amplitude, offset, and noise for our arbitrary waveform output. The other way of using arbitrary waveforms on the RTB is loading them from a file stored either on the RTB itself or from an external USB drive. The RTB supports 2 different file formats. TRF files are a binary format that's used on the RTB for storing reference waveforms, and they're generally not intended for use or analysis outside of the RTB. The more flexible format is CSV, or comma-separated values. Here, the waveform is stored as 2 comma-separated columns, with time and voltage values in scientific notation. This is the recommended format when creating arbitrary waveform files offline or using a separate application. Now that we've covered the basics of using the function generator, let's move on to the pattern generator. The pattern generator uses the P0 through P3 connectors on the front of the RTB to create multi-conductor signal. These signals can also be used for generating serial protocols, such as UART, SPI, I2C, etc. Note that when the pattern generator is inactive, the P0 pin produces a rectangular signal for probe compensation. Please see the presentation Understanding Probe Compensation if you'd like to learn more about how this signal is used to compensate passive probes. Because different types of patterns require different numbers and assignments of pins, a small pop-up window is used to indicate pin assignments for the selected pattern. This is particularly helpful in the case of serial protocols, such as SPI, that use multiple pins. The window can be closed by clicking the X in the upper right corner. The two most basic patterns are the standard square wave and the manual pattern. The square wave pattern is very similar to the pulse waveform in the function generator, with a defined frequency, period, and duty cycle. The manual pattern simply sets each pin to a continuous high or low voltage level. The next pattern is called counter because it produces pulse signals in the same way that a 4-bit counter would produce a divided clock signal. In this type of counter, each bit divides the input clock by a power of 2. To generate a counter pattern, we therefore first specify the input clock frequency, here 100 kHz. The output is then f over 2 on P0, f over 4 on P1, f over 8 on P2, and f over 16 on P3. The default direction is to count up, but this can be changed using the direction parameter. In addition to basic patterns, the RTB can also generate serial data signals such as UART, I2C, SPI, CAN, and LIM protocols. These are predefined patterns that are often used for testing that serial decode parameters have been properly configured. The only configurable parameter for these is the data rate. Similar to arbitrary waveforms, arbitrary patterns are patterns where the timing, spacing, and repetition of the signals can be configured in any arbitrary way. To use an arbitrary pattern, we first use pattern setup to define the bit pattern or sequence, that is, the pattern of zeros and ones. Timing setup is then used to define the timing between these bits or groups of bits. Patterns can also be either saved to or loaded from a file. Finally, to send the pattern, a pattern trigger type is selected. Either repeat the pattern continuously or send it once per click on the manual button. Let's go through the creation of a simple arbitrary pattern. The first step is defining the pattern length, or number of bits in the pattern. The maximum pattern length is 2048 bits. Next, we can select a position in the pattern using the index parameter, and then change its value in hexadecimal using the value parameter. For example, at this index, P0, P1, and P2 are all 1s, and P3 is 0, so the value is hex 07. Values can also be entered or changed in draw mode, which allows defining the bit patterns directly using the touchscreen. In timing setup, we define both the duration of each bit, or the bit time, and the total period of the pattern. By default, the pattern is repeated continuously as shown. If we enable burst mode, the pattern is repeated n times, with a defined idle time between the bursts. After enabling the pattern generator output, we can see each of the 4 patterns by connecting each pin to a different channel on the RTB. Let's end with a brief summary. The internal generator on Rohde and Schwarz RTB2000 series oscilloscopes is enabled by the RTB B6 option and can produce 2 different types of output signals. The first generator type is a function generator, which uses the aux-out B and C connector on the front. This generator produces primarily basic analog type signals, such as sine, rectangular, triangle, etc. These signals can also be modulated using a variety of modulation schemes. The pattern generator uses the P0 through P3 pins and is primarily used for generating digital signals, such as clock signals or serial protocols like UART, I2C, SPI, etc. In addition to these standard signals, both the function and the pattern generator also support the creation of arbitrary, user-defined signals. This concludes our presentation, Getting Started with the RTB2000 Function Generator. If you'd like to learn more about the RTB2000, function generation, modulation, or many of the other topics mentioned in this presentation, please see the links in the video description. Thanks for watching.